Good morning. Welcome to Chemistry with Professor John. Today we'll be talking about alkanes and structure and stereochemistry. There's not much reaction, but we'll mention a few of them. Okay. Well, alkanes are the simplest class of organic compounds that's saturated hydrocarbons, contain carbon and hydrogen only. All right. Formula, I know it's kind of small, but the formula here is for alkane that's not cyclic. The formula is CnH2n plus 2, which means if you have one carbon, you double it, that's 2 times 1 is 2, and you plus 2, that's 4. If you have two carbon, you double it, that will be 4. 2 times 2, that's 4, plus 2, that will be 6. And if you have 3, you do the math, it should be 8, so on and so forth. Okay, now nomenclature. Okay, the first thing you want to do is to find the longest continuous carbon chains and then number them. Okay, and you want to start with the end that's closest to a substituent, a branch. All right, and here are the name of the popular branches, halogens as well, and we have more. Okay, so for example, we have this one. Okay, well, these are condensed formula, so it's kind of hard to see. Okay, but we can do it, right? We can, let's say we go from this end for this one 1, 2, 3, 4, 5, 6, 7, 8, 9. If we go up 6, 7, 8, 6, 7, 8, so it doesn't matter which way we go, it's shorter. Okay, so this one is a branch, that's another branch. Okay, and the first branch is on number 3, so that's good. Now CH2CH3 is called ethyl. Now this one is called complex substituents or branch. It's a complex branch, so we're gonna do 1 again, 2, 3. Okay, so all right. Now 1, 2, 3. So this branch has branches, 2 more branches. So that will be a 1 ethyl, 2 methyl, and it's a 3, so it's a propyl. So that's just the name of that branch. Okay, so we got a 5, we put a 5 dash, because that's a 5 right there, and that's a 3. Okay, so now alphabetical order. So we got a 3 dash ethyl, and then 5 dash, we've got to rewrite the whole thing. 1 ethyl, 2 methyl, propyl, parentheses, and 9 will be no nan. Okay. All right, of course, we can name the other 2. But let's move on to see what else we have in here. Just a little bit of physical property. Alkanes are hydrophobic, obviously, that's not soluble in water. insoluble in water, the boiling point depends on the molecular weight. Okay, they have these are non-polar dispersion force or London force. So that's the weakest force. All right, so there's not much there to worry about. Reaction, there's not much reaction. There's only two that we focus on here. The first one is a combustion reactions. You react with oxygen, you fire it up, you always get CO2 and water. Very difficult to control, meaning once you start it, it will burn, it will react all the way to completions. Now, cracking means breaking it apart. And there's two different kinds. Cracking without hydrogens and cracking with hydrogen, that's hydrocracking. So if you have a big alkane like 12 carbon, double 12, that's 24, plus 2, that's 26. You have a big one. You want to break them apart into smaller alkanes, sometimes more useful, like to make a gasoline mixture, for example. You hit it with, you heat it, and with catalyst, it will break apart into two, a 5 and a 7 carbons, hydrocarbons. Because we don't have enough hydrogen, so this one has to have a double bond. And if you add 1 moles of hydrogens per mole of alkane, you can get both alkanes if you want. Alkane also react with halogens in the presence of heat or light to form halide. So simplest example would be CH4 react with Cl2, give us CH3Cl plus HCl. Okay, so to make halogenated. Now here's a very important concept. It's called conformations. Okay, conformation is the least aggressive way to change the structure, simply by rotations. Okay. Now let's look at ethane with a 2 carbon, 6 hydrogens, and you can see how they arrange. Now if you turn them sideways, that's how it look, one on the left, one on the right. But if you turn the molecules face you will have the front carbon and the rear carbon. The front carbon, a rear carbon, it's a circle. Okay, if you do that, and you look at the hydrogens from the front carbon and the rear carbon, if they line up, we call that angle is 0, theta dihedral angle. Well, that's eclipse, that they lined up, so that's constricted. That's why it's high energy. If you rotate 60 degrees, the rear one, you rotate 60 degrees to the right, you end up with the lower one, lower conformers. And the energy difference is 3 kilocal per mole. And that's called staggered conformations versus eclipse is the top one. Just simply by rotation like that, okay? And these are single bonds, so it's easy to rotate, all right? But the energy difference is still 3 kilocal per mole. That's very significant. All right. And that rotation is known as torsional, is torch. To rotate something, that's torsional energy. And that's 3 kilocal per mole. You don't have to memorize those numbers, but you know, we need to know the eclipse conformation is higher energy. Than this one. High energy, low energy mean more stable. All right. Now, the same molecules, ethane. Now we adding methyl to the rear carbon, replacing actually, instead of hydrogens. We still got eclipse, but this time we got a bigger groups. Okay, so the energy go up. Surprisingly, it's only 10%, 3.3. It's not bad, you know, the difference between eclipse and between the eclipse and the starger. It's only 10%, 3.3. However, we go up, we put another methyl now to the fun, and we got a totally eclipse. Okay, that's 5 kilocal per mole, and then it goes from there. And you go eclipse conformations, and then gouge, which is basically starger. Okay, the gauge is 0.9, and then the lowest energy one is the anti-conformations. Anti-conformation is the lowest one. Okay, and the highest one is the totally eclipsed one, 5 kilocal per mole difference. That's pretty cool. Now notice that we draw when we draw the structure, we always do zigzag, and that's just because we want to spread everything out to make them anti conformations, because simply that's the most stable. Okay. All right. It's a couple for you guys to practice here, and then next one we'll do the cycloalkane, which is very simple actually. Instead of straight chains, we circle them up and connect them and make this cyclic structure, and that's called cycloalkane. For example, 3 carbon we call it cyclopropane, 4 cyclobutane, 5 cyclopentane, that's a 5, and then so on and so forth, 6 cyclohexane instead of just hexane because it's closed up. So each carbon, notice for the cyclo, for all the cyclo, each carbon is a CH2. All right. And if you got a branch, no problem. You know, one branch, you don't have to numbers, make it easy. Like this one branch, you just call methylcyclopentane. If you got 2 or more branches, then you number them. And that's another cool thing is cis versus trans. Trans mean opposite. You see the 2 methyl are opposite on the opposite sides, one on the top, one on the bottom. Cis, the 2 methyls on the same side. You can also look at the hydrogens. Whatever the name is, like 1,2-dimethylcyclopentane, you just throw in a cis or a trans, so that way we can tell the difference between the two. In terms of the ring strand, the best one will be the 5 and the 6 member ring, because the bond angle is closer to 109.5. That's tetrahedral bond angle. But anything smaller like cyclopropane, cyclobutane, those are really constricted. That's why they're not stable. But you get to cyclopentane and cyclohexane, those are the best. Okay, for cyclohexanes, already stable, the chair, when the molecule is not going to be flat, it's going to fold, bend it to the chair. We call it a chair conformations, which spread out the hydrogens. So we got 2 different kinds, the axial hydrogens and equatorial hydrogens. And so notice on this, the chair are the lowest energy, and of course we got the half chair, like one side got flat out, a little bit higher energy, and in between we got the boat, which is lower than the half chair but higher than the twist chair, and the twist chair is higher higher than the chair in terms of energy. All right. The rest of them you can take a look. You when you have the branches. When you have the branches, notice the big one. If you have the big branch on the side or equatorial, that's more stable, more favorable than the one that's vertically. Like this one is really cool, like dimethyl 613 dimethyl cyclohexane. You got the 2-methyl on the left side, um, 2-methyl on the left side, both vertical, so they're in each other way, so the energy is way high. You know, that's at least 5 kilocalories per mole for the methyl-methyl interactions. Too close. Okay, on the other one, the one on the right, when you look on the right, the 2 methyls are far away. That's equatorial. So they're more favorable, more stable. All right, thank you guys, and see you in the next video.